Should have 3/6 out. It's not a salmon colored. In the beginning, it's probably going to be more of a skill for you. The problem is, what are we going to do if we have a composite function? And the Tootsie Roll Pop is going to help us to understand what we're doing, not necessarily how to put it together, but what's happening inside. So what if you have f of g of x? And you are missing a page in your handout, so I have extra paper. And I want to find the derivative of that. If you've noticed, we have not done composite functions. So here's an example of a rate of change. These are rates, how fast we're moving. How many licks does it take to get to the center of a Tootsie Roll Pop? And you could talk about the rate at which you're licking the Tootsie Roll Pops. Some I see are all gone. Okay, so this is an example from a long time ago. I don't think I have any Sues in my class anymore. Sue can run 3 times as fast as Matt, and Matt can run twice as fast as me. How many times faster can Sue run than me? 6. Why? You took Sue's rate times Matt's rate, and so it's 6 times. Well, that's what we're going to do when we do composite functions. We multiply the rates together. Now, we have to understand that this d dx is an operator. When you see dy dx, you are really saying it's the derivative of y with respect to x. A lot of you will confuse it. We will be working on it. This is going to be a process. It's not going to happen overnight. For some of you it will, for others it won't. So I want to take the derivative with respect to x. I could talk about how a function changes as the time changes, for instance. A derivative is a ratio of change, a ratio of 2 changes, actually. So I want to find the derivative of this function, x squared minus 3x plus 4 to the 60. We could expand it. I don't think I want to do that. It would probably take a full sheet of paper to expand that out, multiply it out. I could use my CAS calculator and do it. Or we could just take the derivative as written. Now I have a separate sheet here, someplace. There it is. And I want to find the derivative with respect to x. Here's how you do it. This is like the Tootsie Roll Pop. First you have the one on the Tootsie Roll Pop. You have the wrapper, right? Then you have the what? You have the candy, right? And then you have the Tootsie Roll. Okay, this is like h of g of f of x. It's 3 functions. It's composite. When you take the wrapper off, does the candy change? No. When you eat the candy, does the Tootsie Roll part change? No. So here's how you do it. You first take the derivative of the outer function. This is taking the wrapper off. I have this happening. I see what? 60th power. What about inside? You see a what? You see a quadratic, right? So I have 2 things happening. I have a quadratic. I'm going to raise to the 60th power. So the derivative of this is going to be, I call this y, is going to be 60 times, now Grant, pay attention, whatever's in there to the 59th power. Does the candy change when you take the wrapper off? No. So this does not change. It's x squared minus 3x plus 4. And unfortunately, it's not going to be enough. I can prove it to you with another example. But then we have to do the derivative now of the inside function. You've got the wrapper off. Now we got to take the derivative of the candy. So I need the derivative of this part. What's the derivative of that? You just multiply them. 2x minus 3. And there's no way to simplify that. Leave your answer. So it's actually more important now to be looking at solutions online, because the answers in the back of the book will be simplified. Sometimes they'll use trig identities, and then you really have to do a lot of work, and the assignment will take you hours. And I don't want that. I want to see if you can do the chain rule. So you do the derivative of the outside function times the derivative of the inside. What you're doing when you take the derivative of the outside function, you're taking the derivative of this power with respect to that function that's in there. And then you're going to take the derivative of the function that's in there with respect to x. Example of this, let's say I'm blowing up a balloon. And I want to see how the volume changes, not as the radius changes, but I want to see, Grant, how the volume changes as time changes. Grant, guys. Okay, when I take the derivative of this with respect to time, do you remember what we can do with the derivative operator? We can pass it through that constant. You can ignore the constant. I'll come back and remind you about why that is later. Right now, we're just going to put this back out here, and so it's equal to 4 pi over 3. Now, I want the derivative of r cubed, but with respect to time. First, I'm going to do the derivative of the outside function of r cubed with respect to r cubed. And then I'm going to take the derivative of the inside function with respect to time. Sorry, I said this wrong. The derivative of r cubed with respect to the inside function. Now, let's say you don't know any calculus. You're just looking at this algebraically. What happens to drs? They cancel. That's what they look like mathematically. It's not exactly right, but that's okay. Gets the idea here. When you say that the derivative of r cubed, what is the derivative of r cubed? 3r squared. That's with respect to r. So if I change time, what's going to happen to the radius of my balloon if I'm blowing it up? It's going to get bigger. That's going to change, right? And then as the radius changes, what happens to the volume? It changes. And that's how we chain these things together. Don't worry, this is an intro. You'll be able to, I think you'll be able to do the problems. My goal is that you should be able to do the problems when you leave here. You might not fully understand why it works and what we're doing. But you'll be able to do that. When we get to implicit differentiation, the ahas will come. Hopefully the ahas come sooner, but we'll just see. So first I have to do the derivative of the cubic with respect to what's in there, which is r. And then I have to see how r changes as time changes. So if I go back to the very first sheet, which you have, how do we say that? Can I just cut that? There it is. A derivative of a composite function. Let me make this simpler. The derivative of, with respect to x, of f of g. Okay, Grant? Is the derivative of the outside function with respect to what's in there. What's in there is g. So I take the wrapper off with respect to the candy. Again, I eat the candy, so I find the change in the candy with respect to the Tootsie Roll. And so it's with respect to what? X. And you can see that the DGs would cancel. I see that clearer than I can see that with all the parentheses. It's not a big deal. The question is, can we do it? That's a bigger question. You will need another piece of paper because our first examples are not in your handout for some reason. So if you would like some more paper, I have paper here. So if anybody needs paper, yeah. It's all punched and everything. It's me messing up on copies. All alone back here. Hey, congratulations. That's right. And I don't have the video up from last Friday, but I'll have to get that up. You're all alone, too. Where are these people? Jay, can you come grab a piece? You took both. That's okay. Oh, you got paper. You may prefer lined paper. Okay. You got to go to the next page. We're going to do this next problem two ways. Because we can. And then maybe you'll believe the chain rule a little more. You see, I can do this two ways. I don't need, that's a composite function. I don't need the chain rule. Because what is this equal to? You know how to multiply that out, right? 3x plus 2 times 3x plus 2. 9x squared. But I have 6 twice. So it's 12x plus 4. So if I take the derivative of that with respect to x, of this whole thing, what is the derivative of 9x squared? 18x plus, whoops, press the x. Now, do you believe that? I FOILed it outright, I multiplied it outright, took the derivative right. Okay, so that looks good. And you believe that that's right. The thing is about math is that things always have to be, no matter how you do it, you have to come out with the same result. Even they might do it a different way. Let's do the chain rule on this now and see what happens. And your initial response might be this. What's the derivative of that squaring? What's the outer function? It's something squared, so it's 2 times 3x plus 2. If I multiply that out, do I get 18x plus 12? Which I know is correct. No. What's missing? You would get 6x plus 4, and to get from 6x plus 4 to 18x plus 12, you're missing a factor of 3. And where is this 3 coming from? The derivative of the inside function. So when you do the derivative of the outside, does the inside change? No. So that's exactly the same. And we can do this one 2 ways too. The third one, I can't do 2 ways. Well, I probably could. It just doesn't look like it'd be fun to do. Okay. Now, there are some trig identities you need to know. Here's one of them. The sine of 2x. Now, your calculator will always put the parentheses in, but the AP people don't always. But that's 2 sine of x cosine of x. And we need to know the cosine of 2x, which is cosine squared of x minus sine squared of x. And you need to also know that sine squared of x plus cosine squared of x equals what? 1. Those are the only 3 you need to know. Back in the 80s, if you go back and look at the exams in the 80s and early 90s, you had to know more trig identities. But we didn't have calculators on the exam until 91. So we did have to know identities. Now we don't, so there's much less emphasis. And you shouldn't see anything other than one of those 3 on the exam. So let's pretend I don't know the chain rule, and let's just find the derivative of that. So I'm going to use the trig identity. What is sine of 2x? 2 times the sine of x. What I like about the Inspire is it puts those time signs in there, and so then you can see product rule more easily. The product rule seems to be overlooked. I think if I don't put the time in there, you think of sine x, cosine x as a single function, and it's not. Okay, so we're going to take the derivative with respect to x. I'm going to ignore the 2. So dy dx is equal to 2 times. Now you remember how to do this? It's the sine of x times the derivative of the cosine, which is negative sine of x. Is that right? Plus, and then I'm going to leave the cosine alone times the derivative of the sine, which is what? Cosine of x. And then, just to prove my point, I'm going to simplify that. Don't worry, you can get this thing. Okay. So I don't like my negatives first. Just me. Ask a question if you have a question. Product rule, right? So I'm going to do these first. Because that's what? Cosine squared of x minus sine squared of x. And I put the identity up there. What's that equal to? It's the cosine of 2x, but there's a 2 there. So you can do this problem this way without the chain rule, or we can go up here and do the chain rule. Why don't we do the chain rule? So let's take this one right here. What's the derivative? Y prime. Now you do the derivative of the outer function. What's the derivative of sine? Not negative. The derivative of all the cofunctions are negative. So it's the cosine of 2x times then the derivative of the inner function. Now remember the inner function doesn't change here, and we multiply by the change in the inner function, which is, Abby, question? Yeah. 2. Okay, question back here. Because it's this identity. It's just an identity. Why did I do that? Because I want you to realize that what's true about these 2 derivatives, no matter how I do it, they are the same. They have to be the same. But the only way for me to come up with this answer is to know that identity. Personally, I think the chain rule is easier. And you'll feel that way too. You'll forget to use the chain rule, and I say, remember, chain rule, chain, chain, chain. You know, here's the Franklin. I knew you guys. Okay, let's try this one. This one, there's another tree identity I could use for this, but I'm still going to have a composite function. I'm still going to have to use the chain rule, so why bother? Okay, you ready? So first thing I do is I cover this up. What's the derivative of dy dx? The derivative of cosine is negative sine. A lot of people want to change what's in there. When you take the wrapper off, does the candy change? No. So this still stays x cubed minus 4x. Now you've taken the wrapper off, and now you have to do the derivative of the inside function. And then you're done, which is 3x squared minus 4. You may leave it. I personally like to see this in front only because I want to make sure that I'm not multiplying the angle times the 3x minus 4. It's just clearer that way. But it doesn't matter. You'll have to match it on your multiple choice part of your test. So dy dx is equal to a negative, but it doesn't matter to me. You could distribute that or not. It doesn't matter. Now just make sure that you leave whatever's in there alone. Just think of the Tootsie Roll Pop, that when you take the wrapper off and you eat the candy, whatever's inside doesn't change. It still stays the same. I just changed the order. I just didn't want to see this here because it looks like that's multiplying. Yes, this is multiplying, but it's this multiplying. I could have done that, then it's very clear. I'm not multiplying this angle times that 3x squared minus 4. It's times the sine of the angle. Because when you do a chain rule, you multiply the rates of change together, remember? Sue and Matt. Sue runs 3 times faster than Matt. Matt runs twice as fast as me. These are rates of change, yes. I could have distributed, then it would have been 4 minus 3x squared. It's negative, these are all times. It's like a negative 1 times 2 times 3. It's not distributive. But that's why you want to look at my solutions, because it's going to be nice to see those online. Okay, let's see where we're at. Did that. Okay, you do have this one. Let's try this one. Now, this is a homework problem right out of 3.6. I want to find ds dt. This is on the back of your orange sheet. Oh, no, we'll skip this one. You're right, it's not there. We'll skip this and come back. And there we go. Sorry. Okay, ready? What do we have here? Kind of helps to look at the problem.
Quotient rule.
Good. Somebody saw the quotient rule.
Oh, I did.
And what else do you have? No product. Power rule. Power rule, the 6th power. So what are we going to do? We're going to write this out. So it's 6 times whatever's in there. Does the 2x plus 1 over 3x squared plus 2 change? No. And then we have to do that, don't we? To the what power? 5th. It would be nice if that's all there was to it. I'm just going to move this over so I have room. Okay. Then we'll write out our plan times, and I got to use the quotient rule. Oh, we don't have to write a plan. We can do it, right? Do you remember how to do this? I start in the basement, or main floor, go up, and come back down. This is low. This is high. So it's low d high. 3x squared plus 2. Because this is what they'll also get you on the exam, just reversing that. Times the derivative of the numerator, which is 2. What's next? Minus the numerator times the derivative of the denominator, 6x. Over the square of low we go. Do not square that out. It's a waste of your time. It is a timed exam. Don't do that. Normally I'm going to say not to simplify. I'm going to simplify this inside these parentheses just to make sure you handle the negative sign okay. Because that's where we make the mistake. I've seen it too many times. Okay, this doesn't change. I could do something with the square, 3x squared plus 2 over here. I'm not going to bother with it because that's not where my problem is. The problem is distributing. So what do we get here? 6x squared plus 4. Now, be careful. You have to multiply these together, but don't forget the negative sign. So this is going to be what? Minus 6x times 2x is 12x squared. And then I have to do 6x times 1. And by the way, I've been doing this for years. I still do the arrows. That's going to give you 6x, but don't forget the minus. I think sometimes you guys go through it too fast and you miss those negative signs. That's my guess. All over this. 3x squared plus 2 squared. And if I want to simplify that numerator, I may do so now. What happens with the 6x squared minus 12x squared? Negative 6x squared. What else do I have? I take care of these. Minus 6x plus 4. True, you could factor out a 2. It isn't going to do you any good. And it's all times this thing. And I really can't get it any simpler. The only reason I would want to simplify that more would be if I wanted to substitute in a number. You know, honestly, I'll use my CAS calculator to do that. Where did I get what? Ask. I added these two together. 6x squared minus 12x squared. And then these guys are just there. Now I have a common factor of 2, but it doesn't help me. I mean, I can make that 12 and take out a 2. It just doesn't do me any good. This is not going to reduce. Okay, now for the next one. And this is the one I'm going to let you guys do, but I'm going to give you a little help first. First off, I don't like that sign to the 8. Well, it's really this. Yes. How many functions are in here? 3. Now, be careful. Last class wanted to change whatever was in there. Keep in mind that we take the wrapper off. The candy never changes. And we have to eat the candy. The Tootsie part doesn't change either, does it? So I'm going to walk around and let you guys try this and check you out. Big class, so please check with your neighbors too. And somebody can put this up. There it is. Okay, guys? Let me say it again. Okay, Jay, you guys? First, you take the derivative of the outside function with respect to all of that junk that's in there. The junk doesn't change. So when you take the wrapper off, it's with respect to the candy. Okay, guys? And then you see how the candy changes with respect to the chocolate. So you take the derivative of the sign with respect to that, whatever that is. And then you take the derivative of the inside thing and the candy's gone. Done. We're done. You will have probably no more than 3 things composite-wise. Okay, let's see what else I got. Oh, let's do a couple homework problems. That was it on the sheet, right? Yeah. Now these are homework problems. I don't know if it's on the assignment sheet or not, but it doesn't hurt to do it. Well, it looks hard when it isn't. Right, because you know what? 4 over 3 pi, it's like 4/9. So we're going to take the derivative with respect to t now. I'm going to ignore that constant. Okay, so, Grant, you can help me with this one? Yeah. Good. It's 4 over 3 pi. Just ignore it. You know what the derivative of the sine function is? Cosine. So you're not lost. That's the cosine. Now, would you like me to put parentheses around there? Does that make you see the composite function better? Yes, it does. Times the derivative of 3t. Okay, Ricardo, what's the next derivative? I got to do the derivative of the inside function, which is 3. Plus, now you ignore this. What's the derivative of the cosine function?
5.
Negative sine of, with the parentheses around there, 5t times 5. And what will happen to the 5s? I don't really care. You're done as far as I'm concerned. They would cancel out, right? And the 3's would cancel out. No big deal.
Sure they would.
That's not bad. Let's try the next one. Then we're going to do homework. You should do them. That's the answer. We're not going to simplify these
How'd you get 3?
because it's the derivative. So I'm going to do the derivative with respect to time of the sine of 3t. So it's a composite function. So it's the derivative of the sine of 3t with respect to 3t times the derivative of 3t with respect to t. Do you see how these would cancel? Grant, you asked the question. Pay attention. You see how these would cancel? What is this? This is the cosine of 3t. What's the derivative of 3t with respect to t? Where did the what? Okay, let's try the next one. Number 17. Well, you know what I'm going to do? I'm going to rewrite this. I think what you're doing is that you look at that as a single function, and it is not a single function. It's a product of the sine of x cubed, I'd rather see it that way, times the tangent of 4x. So you have to use the what rule? You have to do the chain rule, but you also have to use the product rule. Okay, so it's the sine of x cubed times the derivative of the tangent of 4x. I'm going to make the plan. I messed up in the last class because I didn't follow my plan. If I had followed my plan, life would have been easier. And this is the tangent of 4x, right? Because I said, oh, I don't need that. But obviously I did. Plus the tangent of 4x times the derivative of the first. I haven't done it yet. First I used the product rule. Now I'm going to use the chain rule because this is a composite function and that's a composite function. You have to do the product rule first. Yes. Can't do the chain rule yet because the only way to do a product is to take the first times the derivative of the second plus the second times the derivative of the first. Okay, so y prime is equal to the sine of x cubed. What's the derivative? Do you guys remember that one? Secant squared.
Shouldn't there be 4 terms? Where's the last?
There's 2.
No, in the what you call it, the product.
There's 2. Terms are separated by plus signs. There's the first term, and then there's the second term.
Oh, the sine of x goes with it. I didn't see the sine of x. That's what.
Okay. So this is secant squared. You should be doing it with me of 4x. Now that's the derivative of the tangent function with respect to 4x. Now you have to take the derivative of 4x with respect to x. So it's times what? 4.
We have a quiz this week.
Yes, we do. We have a quiz on Wednesday. It's a partner quiz, and it includes the chain rule. And you need to know the derivative of your trig functions. So now it's the tangent of 4x. And what's the derivative here? 3 sine of x, quantity squared, or sine squared of x, times the derivative of the inside function, which is cosine of x. That's it.
No, thank you.
You really could talk about the derivative of this really inside function. What's the derivative of x? 1. I will need that later. Yes.
Is it incorrect if we don't do secant squared, but whatever the like sine, cosine are?
Oh, if you change tangent to sine over cosine? No, it's not incorrect. I can recognize those. Okay. Those were all the problems. Questions out of 3.5. We're going to do number 13 together. I'll make my videos the same. And S is equal to, I don't know. We're going to go over some homework questions because this asks for velocity and acceleration and speed and stuff. S is 2 plus 3 sine of t. And we have to know this. It asks for the velocity, the speed, and the acceleration. And it also asks to talk about the particle motion. All we're going to do is decide if it's speeding up or slowing down, because I didn't like that part of the question. B, we're going to do the velocity, speed, and acceleration at t equals pi over 4. This is at t. Okay, so we should know how to find velocity. Adam, do you remember what velocity is? It's ds dt. No, it's the first derivative.
Well, the first derivative of velocity, second derivative of displacement.
No. Velocity is the first derivative of the displacement. And you all drive cars. If you drive at 50 miles per hour, that means in 1 hour you will cover 50 miles. That's a velocity. So what's the derivative of this? Now this is a homework problem. Jay, what's the derivative of 2 plus 3 sine t? What's the derivative of 2? It's 0, because that's the slope. And then I want to do the derivative with respect to time of 3 times the sine of t. Now, I've been telling you can pass the 3 through the operator, but why can I do that? Because it's 3 times the derivative of the sine, which is the cosine of t, right? Plus the sine of t times the derivative of 3. You can always do this, because it's always true. What's the derivative of 3? It's 0. So this term goes to 0. That's why I can just pull the 3 through. Because the derivative of that constant is always going to be 0. Now, what is the speed then? It's the absolute value of 3 cosine t. And generally speaking, unless I want you to know what this thing looks like, they will put it on a graphing calculator section. Grant, how do I do the next part? Acceleration is the derivative of the velocity with respect to time. When you start at a stoplight, your speed is 0, and when you get up to 55 miles per hour, you're going 55. What have you done to the car? So you've changed your velocity because you've accelerated. Okay, so I need the derivative of this line right here. What's the derivative of 3 cosine t? Negative 3 sine of t. This isn't so bad, is it? But you have to know what velocity, acceleration, and speed are. You just have to know it. The only way you're going to get there is to practice. So for part B, I want to evaluate this at pi over 4. So B, what is my velocity at pi over 4? It's, whoops, too much. Now we should know this. It's 3 times the cosine of pi over 4. If this is free response, you would just leave it. Although you would have to know if it's positive or negative. What's the cosine of pi over 4? Here's my triangle. Here's 45 degrees. This side's 1. That side's 1. This is square root of 2. So it's 3 times 1 over the square root of 2, which you could rationalize, which if it were multiple choice would most likely be rationalized. So 3 square root of 2 over 2. Clearly a positive number, right? I don't know if it's speeding up or slowing down. What's the speed then? Guess what? The speed is the absolute value of that. 3 square root of 2 over 2. Okay, what's the acceleration? The acceleration at pi over 4 is this. Negative 3, the sine of pi over 4. What's the sine of pi over 4? It's a 45-45 triangle. It's the same as the cosine. Square root of 2 over 2. And I know that's 0.707 because I did physics over 30 years ago. And we didn't have calculators. And I had to know those. I just knew what those numbers were. I still remember it after 30 years. 0.707. And the cosine of 60 degrees is 0.866. You can check me out if you make sure I'm right. Okay, but this is clearly negative, right? If this is positive and this is negative, what is the object doing? So, and that's what I want you to get out of this part of it. We'll do another particle problem tomorrow. So tomorrow is filled with activities and reviewing and answering questions. Yeah, little worksheets. It's slowing down because A and B are opposite signs. Please be succinct. Don't give us an essay because then we have to weed through it and then we have to make sure we read it correctly. Also, make sure your work is organized, clearly written, because I'm more likely as a grader to make sure I get points to somebody who writes it neatly. It's not, it's not a bias. It just is. If I'm struggling to find your stuff, I don't like to do that. You're better off if everything's nice and clear. Okay, the next one we did was, because we should probably do some homework problems, 21. And we're going to start with a graph on 21. Those of you who did your homework, is it starting to look a little better? Is this helpful? Now don't forget, I'm here in the morning. Hi. Yes. We will, let's see what we do. Oh, I want the equation of the tangent line, and you have to do this, at pi over 4, pi. And I want the normal line. What's normal? That's how you find it. What is normal? Perpendicular. Okay, Grant, you should be writing this down because this is homework problems. Then you have it done. I don't know what the homework quiz is going to look like on this, but it might be nice to have it done. Okay, so I'm going to graph this first. I'm not going to jump into derivatives yet. I want to know what it looks like. Hopefully it's straight. That's straight? Or what? Okay, here's my sine curve. And what's going to happen to my sine curve? I'm going to go up 3. So that's a 3. Trying to make it reasonable. I want to draw the equation of the tangent. I want to write the equation of the tangent line at pi, which is right here. There's the tangent line, which it clearly cuts through the graph. And I also want the normal line, which is perpendicular. Okay? This is a very common question on the AP exam. So how do I write the equation of any line? This is not a hard question. Okay, Ryan? How do I write the equation of any line? You should be doing the problem with me. Y minus y1. I need 100% of you getting this right 100% of the time. It's doable. It is a lot to ask. But it's equal to m, x minus x1. Can m ever be a variable? No. Okay, I want it at x equals pi. I can find the y value. You could look at the picture because I drew a nice picture. What is f of pi? It's equal to the sine of pi plus 3. What is it? Sine of pi is 0, and 0 plus 3 is 3. Now, if this were free response, I would leave it sine of pi plus 3. I would not evaluate it. So it's y minus, but I'm going to ask you to do that until we get practice. 3 is equal to my slope, and it's x minus pi. Now tell me why that's hard. Because I don't know why it's hard. I always start with the equation of the line, and now I have to find the slope. This is the calculus. How do you find the slope? What is slope? It's the derivative of y with respect to x. So the derivative of the sine of x is cosine of x, and the derivative of 3 is 0. And I have to evaluate that at pi. X equals pi. If I don't know what the cosine of pi is, I will draw a graph. So when you get into the exam, I strongly recommend that you just draw the graph of the cosine curve, remembering that this is 2 pi, and we divide these in half. There's pi. What's the cosine of pi? Not 0, -1. So this is equal to -1. So the regular line is y minus 3 equals -1 x minus pi, and the perpendicular is y minus 3 equals 1 x minus pi. Now was that? It's lengthy, but is it hard? It's not even that lengthy, actually. So that's what you have to do. When you get to 23, you either can leave it exact or you can use your calculator. If you're going to use your calculator, always 3 decimal places. I've got nice little pictures in here. You need to practice with some of these just to get the practice in on the derivatives of the special functions. 35, we did 35. Did it in class on Friday. I didn't call it 35, but it's what it is. I'm just looking at it now. And actually, 11 through 20 are the easy ones. Just take the derivative and find the jerk. The jerk is the third derivative. Are there questions? I am here in the morning tomorrow. I will be here after school. I might even have candy. I have a ton of candy.